Hi students, let's talk about the average velocity and the instantaneous velocity. So the situation we have here is we drop a tomato from the top of a 100-foot building. And we watch it fall. It's going to have this parabolic shape as it falls. And then after 2.5 seconds have gone by, what happens? It goes splat on the ground. So the velocity changes as the tomato starts. It gets faster and faster and faster until it hits that ground. So what we can compute is the average velocity over any 2 points in time. And this average velocity will just be the change in position over the change in time. Please look at our graph here. We have graphed along the horizontal or x-axis, we have time in seconds. And then our vertical axis is our height in feet. Velocity is in feet per second. So this will be our units when we compute our average velocity. You can think of it also, we're going to use our delta again to mean the change in delta y over delta x. And what does this look like? Well, that's just the slope. It's like we drew a straight line between any 2 points here. They don't have to be next to each other. And we computed the slope of that line between those 2 points. So the first problem we'll work on is the average velocity of the tomato during its fall, meaning starting at time of 0 with a height of 100 feet to when it splats on the ground after 2.5 seconds, we have a height of 0 because it's on the ground. So you can think of these as x, y ordered pairs from our table here. And our average velocity will be our change in position. So let me start at the second ordered pair, and I could start at the first one. It doesn't matter where we start here. So 0 minus 100, and then divided by 2.5 minus 0. So when I compute this, I'll have negative 100 divided by 2.5, which will be negative 40. And what did I say the units were? Feet per second. It's as if I drew a straight line from this point to our last point and computed the slope of that line. What if we wanted to compute the slope of a different set of points? Well, we could choose whatever points we'd like. So what if we wanted to now talk about the average velocity between 1.0 and 2.0 seconds? So let's come over here to our tomato drop table. And now we're going to use those 2 ordered pairs. So at 1 second, the height of the tomato was 84 feet. And at 2 seconds, the height of the tomato was 36 feet. So we're going to do the same thing, calculate our average velocity. By taking the change in y. So as I said, you could start with this point, this ordered pair, or this one. Doesn't matter. Let me go ahead and start with the first one. So 84 minus 36. And then divided by, I have to take the time 1.0 from this point, since that's what I started with, minus 2.0. So 84 minus 36 is 48. 1 minus 2 will be negative 1. So this will be negative 48 feet per second. the velocity negative, again, because it's going down, and the velocity was faster, it was moving faster at this point than it was for the whole thing because, once again, the tomato's starting slow and then it increases its speed. Now, what if we wanted to get the actual velocity, the instantaneous velocity, at any point in time? Like right here at time equals 1 second, what is the velocity of the tomato right there at that point? Well, let's talk about that. So what if we wanted to compute the instantaneous velocity at 1 second? At that precise moment of time, what is the velocity at that point? Notice that we've been talking about average velocity between any 2 points in time. But here we want the instantaneous velocity at this exact time, which is that point right there on the graph. Well, what we really want here is the slope of the tangent line at that point in time. And I wouldn't be limited to just that time. I could really draw tangent lines at any point, any of these points. Now keep in mind, reminder, what a tangent line is. A tangent line is up against the curve. It's only touching one point on the curve. Unlike a secant line, which is what our average velocity was showing, that we were drawing a line between any 2 points, that's called a secant line. For example, if I drew a line between t equals 1 second and t equals 2 seconds, this line would connect these 2 points. It would be below the curve. It would be like right here. So this tangent line is going to allow us to compute very accurately the instantaneous velocity at exactly 1 second at time. So I'm going to use now a little bit of calculus terminology. The instantaneous velocity is defined to be the limit, and I'm going to use a little bit of terminology I haven't talked about yet, as h approaches 0 of f of x plus h minus f of x divided by h. Now what that means here, this h is going to be a little tiny bit farther away from my starting point. I'm going to shrink basically that interval smaller and smaller and smaller until I'm really right on that point. And calculus is going to allow me to compute this limit. And what this will end up being for us is the derivative of the function. Bye, students.